So my name is Saikat Banerjee. I'm an engineering manager here at AWS. I run a team that focuses on .NET innovations. And we're doing a bunch of things around .NET open source. And one of the things that we did this year, we'll talk a lot about that around Lambda and native AOT. But before that, I'm joined by Bo.
Yeah, hi, I'm Bo Goss, Senior Software Development Engineer on Saikat's team.
Yeah, so today we'll talk a lot about .NET on Lambda and the performance that you can have on Lambda and the problems that customers face and ways to fix them. So let's get started. Oh, okay. So nobody likes waiting for loading times, right? Our customers hate it. You hate it. We hate it too. So, and we've been hearing a lot of customer complaints about when they hit cold starts, the performance issues that customers hit when starting new apps, and the way Lambda is designed, that becomes a bigger problem. And on Monday, we launched Snap Start for Java. And this was our attempt to see how we can improve cold starts for .NET applications in Lambda. So moving on, this is the brief agenda. It's kind of packed, and we'll try to keep the time. And we'll talk about the Lambda basics, which I'm pretty sure everybody's aware what Lambda functions are. Then we'll talk about why cold starts happen and what's the architectural nuance behind Lambda that makes Lambda so attractive, yet cause cold starts for compiled languages like .NET and Java. And then we'll talk about some strategies around preventing cold starts for AWS Lambda. And then we'll come back saying that why some of these strategies are sometimes overkill, sometimes unreliable, and talk about programmable ways to reduce Lambda cold starts for .NET. And this year, we have been focusing and investing a lot around native AOT, and we've launched tooling around native AOT for you to use on AWS Lambda. We'll do a demo. Bo will take over when we come to that section. He primarily worked on native AOT for the whole year. So probably if there's anybody on AWS who understands native AOT really well, it's him. And he will do the demo on like native AOT, how to use it on AWS Lambda using our tools. And also, there would be a drag race between native AOT and JIT compiled Lambda and see the performance benefits in different scenarios. And then we'll basically end the talk around like what are the features today and what we probably think about improving in the future. Oh, oops. So Lambda basics, I'm not going to spend too much time, as I'm pretty sure you're aware of Lambda. None of us like patching servers. That's why Lambda came into being. Serverless, you can spin up small workloads, and you can do pretty much almost everything these days on Lambdas, from data processing at scale to like web and mobile backends, and multiple basic API stuff. Like you could probably spin up Lambdas for almost anything. But one thing I do want to cover is how Lambdas work, right? So, and why it is important to improve performance of Lambda. It's not just the end user experience. Of course, that's probably top of mind for you, but also but also I think the performance is what drives your cost, right? So traditionally, when we thought about VMs, we thought about a vertical structure where if you throw in more resources, your cost goes up and your performance is improved. But not so much for Lambdas, because when it comes to a Lambda, it's like an optimization problem between resources and performance. and resources, performance, and cost. And this we can explain this through this graph of power tuning. So this is a tool that you can use today, and you see the red line in this graph is the execution time, and this gets reduced based on how much resources or memory you throw at your Lambda, and the blue line is your cost. So as you see, if you throw in more and more resources, of course your cost probably could go up at the very end, but if you see towards the beginning of the curve, when it starts declining, the cost is actually higher. So the reason is that Lambda cost is not only dependent on the amount of resources you use, it is also dependent on how long you use those resources. So it is a pay-as-you-go structure. So if your Lambda is taking longer to get invoked and to complete, you are paying for the resources for that duration. So you can increase the resources, but have a lesser invocation time that will actually reduce your cost. So this is probably why you would want to improve performance of your Lambda if end user experience was not focused for you. So why does serverless cold start, like what are serverless cold starts and why do they happen? So the diagram on the right shows how a Lambda starts. What's the Lambda's life cycle? So Lambda starts so there's an init phase of Lambda where your infrastructure is getting provisioned. Then there's the invoke phase. So the init phase is when your function constructors, the Lambda constructor, is getting called. And then the invoke phase is when your handler is getting called. And then the shutdown happens where it's not too much of an impact of performance for running Lambda. So the cold starts actually is the init phase, which takes more time to launch a .NET or a Java application. So if we look at, so this is a sample Lambda function. We have just added like a 2-second sleep in the constructor, a 3-second sleep in the function handler. And you see the times it took to invoke the handler and the constructor in the cold start is 420 milliseconds and 348 milliseconds. And the warm start, it took 4 milliseconds for it to get hit. And this is like a very simple Lambda. Like this is only 2 lines of code, doing nothing basically. But if you see this slide, right? So you can see that the Lambda cold start actually takes more time in the invoke phase, even more than the warm start. Forget about the init phase. Of course, that's a whole different phase that you have, like it goes through. But even the invoke phase, it takes more time. That is, the reason is the JIT compiler actually does a few operations while loading your Lambda, or while basically transforming your IL code to native code, which it uses later because it's basically running on native code. And through native AOT, which Bo will talk about, we're doing a lot of front loading of that compilation ahead of time so that you can just use the native code. So when we talk about the CPU and memory, when you throw more memory at your Lambda, why does it perform better? And when does it perform better? It performs better when you have CPU-intensive tasks. It would not perform as well if you have network-intensive tasks or if you have disk operations per se, right? So if you have a high operational load on your Lambda, it will perform better if you throw in more memory, more CPU. So let's talk about some of the methodologies or strategies that are there today to kind of prevent cold starts, or something that you can find online to prevent cold starts to even happen. So one of the hacks that I think has been like blogged about quite a lot is the scheduled ping. So we feel it is unreliable because the infrastructure behind Lambda, micro VMs or containers that get spun up and killed based on when Lambda is getting instantiated, is pretty non-deterministic because it depends on several parameters like what's the size of your Lambda, how many times it is getting invoked, and a lot of parameters. So you cannot really predict when your Lambda infrastructure is going to die off, right? So the schedule ping may work. Like if you put a schedule ping of say five minutes at a periodic interval of 5 minutes, it may work, but it might as well not work because maybe in 2 minutes your Lambda gets the infrastructure behind your Lambda gets killed. So how do you so when you read this, use this with caution because this is very, very unreliable in our opinion. So the second area is provision concurrency. So if you have seen, so let's talk about provision concurrency. But before that, you might know there is a thing called reserved concurrency for your Lambda, which is account-based concurrency that you can provision for your Lambda. So that I think the default value is 1,000, and you can probably call AWS support to increase that quota. And you can use the 1,000 concurrent request for any of your Lambdas in the account. But that causes a scale problem that when your app, say, needs to scale at 5 p.m. every day, so you need a scheduled scaling activity to happen on your Lambda. So you can use provision concurrency for that, and also utilization-based scaling, which is nothing but auto-scaling feature that you can use on, like, say, ECS, for example. You can use it for Lambda as well. So what it does is it basically figures out what is how many times your Lambda is getting invoked, and based on that, it pre-provisions resources specifically for that Lambda function you set this up for. But provision concurrency is a scaling solution. It's not a solution to improve performance or improve cold start performance. Think about this use case where you have a sporadically utilized Lambda function. You don't need scaling. Your Lambda function is getting hit probably, say, every 10 minutes or so. It's a sporadically used Lambda function. For that, if you use provision concurrency, you're potentially looking at a larger cost than what you would have if you took other measures in improving your Lambda function. So the cost structure is same as Lambda, but obviously you pay more for the provisioned resources that you put behind your Lambda function. So we think that this is a great solution for scaling, but not so much for improving cold starts, although it works. Of course, it will work because your Lambda is always warm. So there are other strategies to reducing cold start durations. So one is code optimization. So there are certain best practices that you can take to actually improve the performance of your Lambda just by writing like better code and better Lambda code. So the main thing is do not duplicate work in the handler. If you need some work to be done once when the Lambda starts, for example, deserializing your config file, for example, you should do that in your constructor so that it happens once and you can use it for every other invoke as long as the Lambda is warm. The second one is use small functions. So you can use multi-controller APIs, you can design them, but it's hard to maintain in an isolated way, hard to maintain it in like Lambda-specific isolated way, for which you can use the .NET Annotations Lambda framework. You can use multi-controller functions, but also use the Lambda features in the most like best practices way. The third one is hosting static content in Amazon S3 or somewhere else other than doing the disk read during initiating a Lambda. So you can probably lazy load some content into your code. And that is, I think, a best practice not only for Lambda, but for any web application performance. I think these days everybody does that. The final one is that previously we've always used, we've used Newtonsoft JSON. The system text JSON, I think recently system text JSON can actually do reflection-free serialization through code generation. So that supports the native AOT use case, and I think Bo will cover that when he talks about it. One other thing that is already available today in the Lambda blueprints is ready to run. So ready to run, we think, and also we have seen it in the benchmarks that we have run, we've seen that this is kind of a middle ground between JIT and native AOT. So this has the goodness and some of the problems of JIT compilation. And it contains both IL and native code that makes the binary size almost 4 times larger. So when you actually load it from the disk, when you load the binary from the disk into memory, that takes time for the ready-to-run binary. So there are certain flexibilities, obviously, because you have IL code and you have an opportunity to do the runtime compilation into native code. So the dependencies, the reflection problems that you see in native AOT, you don't see them so much in ready-to-run. So with that, I'll hand it over to Bo to talk about native AOT and do the demos.
Yeah, thank you. So I'm super excited about native AOT. I think it's going to be kind of a game changer for .NET in the coming years. But first, let's just dive into JIT compiling real quick to recap some of the things that were mentioned already, but just to get a good understanding of what we're giving up with native AOT and the current state of things today. So with .NET, there's many languages, such as in the diagram here, you can see C#, VB, and F#. And all of these get compiled to intermediate language code with their metadata, sometimes called MSIL or CIL for Microsoft Intermediate Language or Common Intermediate Language. And that code is kind of independent of the operating system that you're going to run on, where the .NET runtime can actually take it and, with the JIT compiler or the just-in-time compiler, compile that IL code to machine native code in the execution environment that it's needed in, such as Linux or Windows or wherever you happen to be. The JIT compiler gives you a lot of flexibility, like we mentioned. You can dynamically link in assemblies at runtime because it can compile code at runtime to be executed on the physical machine. It gives you that flexibility to link in code at runtime or even generate code at runtime with emitting code and reflection and things like that. However, this does incur some startup costs because, as we've mentioned, you need to actually JIT that IL code at runtime. And I want to point out the loop here. You can see we're kind of trying to imply that the JIT is always running. It's always trying to optimize your code. One interesting code optimization, just to give you an example, would be like inlining a function call. So if you have one function that's calling a second function, there's overhead to physically jumping to a new spot in memory on the CPU. And what the JIT compiler can do over time as your code is running and realizes that it'd be more efficient to actually move that second function that you're jumping to into the first function and not do the CPU jump at all. And it saves that jump overhead. And then that's just one example of the many complex things the JIT compiler can do at runtime in optimizing your code. So Why native AOT and what is native AOT exactly? So it was released with .NET 7 officially for support for console apps. It's been an evolution from a lot of native type things. Originally there was the experiment with CoreRT, and other forms of .NET have had somewhat native compilation, but this is kind of the first mainstream release of all of .NET going native. You can use it with the publish AOT property. It's basically just a flag to turn on and tell the compiler I want to compile for native AOT. You can set that property in your project file, or you can pass it in through the command line. And as we've implied, basically, all of the compilation to machine code happens ahead of time, right? That's the AOT, and native AOT is ahead of time. So you're front-loading a lot of that work and the compiler optimizations that JIT could potentially do, and you're finalizing the executable assembly. But at runtime, when you go to run it, it obviously doesn't have the JIT compiler in there anymore, so you're saving memory in your process to not need that anymore. And you can get immediately into executing your actual code rather than getting into the JIT compiler to generate machine code. So we think it's really exciting for Lambda specifically because of the cold start reductions, the reduction in cold start times that we've seen in our testing. So anywhere from 20% on the low end to 70% on the high end as compared to actual ready to run, which is already better than pure JITted .NET code. So to get a little example, we'll switch to the demo computer here, and I'll show you a real quick demo first. Okay, perfect. So this is the serverless drag race. This is running a local web app, but that's not important. What's important is I've deployed 2 Lambdas with identical code, except one was published with native AOT, and one was published with ready to run. That's the only difference between the 2 Lambdas deployed to my account. And this will give you a visual representation of the loading or reaction times of these cold starts. So on the left, we have ready to run, and on the right, we have native AOT. And I'm gonna start the race here, and you'll be able to see as logos will pop in under the text as each one is done with its processing. So, okay, that was a really extreme example here. That's a huge improvement for native AOT. You won't necessarily see that big of a difference every time. It depends a little on networking. You know, this is a real live demo. But yeah, that's an extreme example. What's really going on in these Lambdas, just to give you an idea for the work they're doing, they are each basically serializing an object, writing it to S3, deserializing an object, and listing objects in S3. So just some SDK calls, some S3 usage, serialization usage, just representing some common code that you would execute. So the code you execute and the code in your Lambda is obviously going to change and make a big impact on how impactful native AOT is. As we've kind of referred to earlier, if you're very network bound, you're not necessarily going to see a huge improvement as much as if you are more CPU bound or just have a lot of dependencies that all need to be JITted at runtime. So we'll give it one more go here. I'll reset it for a cold start. If you're curious and want to try this out yourself with your own Lambdas, an easy way to reset your Lambda for a guaranteed cold start is to change anything in the config of that Lambda. So you can go into the console, for example, and just change the timeout by a second. That's what I'm doing here. So the timeouts in these are way higher than we need them to be, and I just move them around by a second, and that forces a Lambda to reinitialize the Lambdas for a cold start. So if you want to try it yourself. So we'll do one more. So again, it's very noticeable improvement with native AOT. I think it's honestly game-changing when it comes to cold starts and .NET in general. I think native AOT is going to be an important part of .NET in the future as more and more libraries and companies support it in the ways, especially around trimming, which we'll get into. And just to show you some warm starts here, the warm starts kind of go back and forth. They're not as, right there, pretty close. They're not as impactful because they're both warm already. They're both kind of running machine code that's already ready to go at that point, so less difference. Although, again, the JIT compiler is not in memory. It's not in process anymore, so it is a little less intense on the resources once you have it loaded up. Okay, so these were just some ad hoc numbers you could see here. Hopefully you can read the milliseconds we were looking at. But we're going to switch back to the slides now, and I'll give you some more statistically accurate real tests we did. Okay. So these numbers come from this GitHub repo at the bottom of the page. You can see linked. It's a really cool repo that does kind of a standard benchmark with DynamoDB, and it does it. There's other repositories in the AWS samples group under GitHub that do the same benchmark across different frameworks and languages, so you can compare kind of to Node.js and Java and see. Here we're showing .NET 3.1, 6, and 7 native AOT, but we even have like all kinds of .NET benchmarks in there, so you can see both cold and warm start times. We just picked out some here to show. But the code that this is running is totally different from the demo I just showed. This is DynamoDB, where the code is basically doing a write to the database, a read, an update, and a delete, like all those things. So the x-axis here is kind of weird, showing the 50th percentile, the 90th percentile, and the 99th percentile. And the vertical axis is the cold start time in milliseconds. So you can see in the median, like 50 percentile case, native AOT beats .NET 6 and .NET 3.1. And .NET 6 is faster than .NET 3.1, and just plain .NET 7 now is even faster than .NET 6. They've made a lot of performance improvements with .NET 7 too, without native AOT. But then, interestingly, as we take a higher and higher percentile, so the worst 1% of cold starts on the right, that's where native AOT really shows its consistency, because it's not doing that JIT at runtime and not dependent on more work happening. It's just consistently ready to go from the beginning. And to show the warm starts, again, like the live demo, a little less impactful for warm starts, especially in the 50th percentile. But again, we see a little bit of benefit for the 99th percentile here. But again, we're talking about what a less than 10 millisecond difference there. So to just explain and talk a little bit more about native AOT outside of the performance category, there are other benefits that people could get from native AOT, and maybe you can use in some other use case. So because IL code is very easily decompiled, you may have used JetBrains tool to decompile IL code back to C# or something like that and just get right into it. It makes it incredibly easy. So because this is compiled to machine code, it's arguably better obfuscated and harder to decompile and reverse engineer, if you will. There's also the case where JIT is banned on some platforms. I think at one point, iOS didn't allow JITted programs to run on it, and so this is a way .NET could be run on platforms that don't allow JIT. It also, as we've said before, has lower memory usage and smaller package sizes. So just in general, even if you have a steady state app that's not necessarily cold starting all the time, you can still get that benefit of needing less memory and less resources to run a native AOT app versus a JIT app. And then lastly, another benefit some people could get into is just that interoperability with other native native libraries and applications. So you can use native AOT to publish shared or static libraries and interact with other like C++ apps and whatnot. So now we'll switch back to the demo computer here, and I will show you how you can get started with native AOT. We've got some blueprints, and we'll go through, I'll explain what's going on behind the scenes and kind of dig into some of the details so you can really understand what has to happen, how it works, and how you can maybe apply it to your own Lambdas. So let's close this one. Okay, so this is Visual Studio 2022, and I'm just going to create a new project. If you have the AWS toolkit for Visual Studio installed, which I hope a lot of you do, it will come with project templates. So we have two categories here. We have Lambda and serverless project types. And the difference being Lambda is just a simple Lambda function by itself that could get deployed as a zip file to the Lambda. And the serverless templates have a CloudFormation stack behind them, and so they can be a little more complex and control your infrastructure as you go. I'm going to select the serverless one just because it has a little more interesting request and response type here. So if you search for native, you'll see we have .NET 7 native AOT, and this is C#, but we actually also support F# blueprints and templates for all of our templates for native AOT here. We'll use the default project name, set this up on my account. And okay, so here's our solution. Hopefully this can be read, but it's basically just a project file, a single CS file, and then your template file and your defaults JSON, which control how you deploy the Lambda to Lambda. I want to start with the project file because it's important to understand how we're actually deploying .NET 7 native AOT to Lambda, right? Lambda doesn't have a .NET 7 managed runtime. And even if it did, we wouldn't necessarily use it because with native AOT, you're combining the runtime into your binary. We're generating a standalone machine code executable binary. And so we don't actually need the .NET runtime on our execution environment. And so if you've created Lambdas, you most likely started with just a library that defines a handler and then told the Lambda where the handler was in that library with the double colon thing. But in this case, we're actually creating an output type of exe here. So it's a standalone app that can run. And obviously we're targeting .NET 7. Like I mentioned before, we're setting publish AOT to true. That's how we actually turn on native AOT. Could be done through the command line, like I said before, too. And then strip symbols is also related to native AOT. This tells the compiler, in the case that you're compiling for Linux, right, to strip the runtime debugging symbols into their own file. And this happens by default on Windows. You're probably familiar with the PDB file for debugging, but on Linux, that's normally bundled into the executable. And so this strips that out, which allows us to not upload that to Lambda, because that'll over double your package size and cause more upload and download and slowness there. Another important thing to call out in any custom runtime, really, this is going to be a custom runtime. Like I said, we're going to run this on the standard provided AL2 Lambda, no .NET installed. But you need to, by convention, Lambda looks for an assembly called bootstrap. So we're just setting that here so that when we publish, it will be called Bootstrap as the file name, and Lambda will be able to find it. It's a common, if you're going to convert your existing Lambdas to native AOT, just make sure you do that, because the blueprints obviously all come like that, but you might forget and then upload it, and it'll complain about not finding a Bootstrap file. The other thing I wanted to show here was that we're using this library called Amazon Lambda Runtime Support, which is another library you probably haven't used unless you've run a custom runtime on .NET on Lambda. This library it provides all the kind of boilerplate and setup code you need to actually interact with the Lambda execution environment. And I'll show you how that's used in the main method in a second. And I also want to call out, we were including an RDXML file here, which is the runtime directives file and tells the compiler, it kind of hints at the compiler to what to trim and not trim. And so we haven't talked about trimming yet, so let's explain that briefly. By default, native AOT is always trimmed. If it wasn't, you'd have a gigantic executable because it would have the entire .NET runtime in it and every library you use. And so what the compiler does is it tries to statically analyze your code and figure out which types are actually needed, which methods are needed, which classes are needed, and which ones aren't used. And it'll trim the ones out that aren't used. It usually does a really good job, but sometimes, just because of the way your code works and it's very dynamic, it might not even be possible for the compiler to understand which types will be used at runtime and which types won't. You can think of the example where you take input from the user and they provide a type name, and then you use reflection to initialize that type, right? The compiler's not going to know which types are going to be typed into the input or not. However, the RDXML was more used for native AOT was in development, but we're actually going to remove this for now and use publish a trim mode of partial. So if we do trim mode partial, this is as opposed to trim mode of full, which is the default in .NET 7. Partial will only trim assemblies that are marked as trimmable. So it's a little safer, but it won't trim as much and you will have a bigger package size. But for getting started with a hello world and maybe just trying it out, it's a little easier to try partial for now. But as you productionalize native AOT, you're going to want to pay more attention to trimming and try to trim your app as best you can and get rid of all the trim warnings that you can, because when you have a trim warning, the compiler is basically saying there's a possibility you're going to call and need a type that I trimmed out, and so that could cause a runtime error, which you've got to be careful with. Okay, so that covers everything in the project file, and let's look at the actual code here in the CS file. The main, let me just get this so we can focus on the code. The main difference, because we're self-bootstrapping here, we have a main method, and it's actually pretty easy with the Lambda runtime support library I mentioned. It gives you this Lambda bootstrap builder, and you just call create, you pass it your handler, which is just like you would do with a normal library Lambda. You have to tell it which handler. And then the only other thing we provide is a serializer. So this actually isn't the default serializer. This is the system text JSON, like source code generated serializer, which is defined at the bottom and pretty easy to use. So here is how you create one of those. You just create a partial class that extends the JSON serializer context and attribute it with the types you want to serialize. So we're telling this JSON serializer context that, because we're going to take an API gateway proxy request and return a response, we need to know how to serialize those. And when you use this JSON serializer context here, it will actually, at compile time, generate dedicated code just for serializing those types. And that's different from the default serializer if you use system.json, where it will use reflection to try to figure out the type and learn about the type and serialize and deserialize that way. And that reflection is not only slower, this is just a good thing to use in general for performance, but it also is really important for native AOT because reflection is one of those things where you're going to run into trimming problems. You're going to try to reflect on a type and maybe a method of a type, and that method's not going to be there. And so by eliminating reflection, you're really eliminating the chance of running into a runtime error caused by trimming. So we just inject that serializer, and we inject the handler, and the handler is just your standard Lambda handler as you would have any Lambda handler here. This one takes, like I said, the API gateway proxy request and a Lambda context, basically just does a hello world, and that's it. So that's the code that's important for native AOT in this example, and let's try to deploy this here. And I can explain the complexity of deployments and what we actually had to do and how we changed the tools to support this. So if we publish to Lambda here, just give it a unique name there, put it in my bucket. So this might be a little small to see, but right here we're calling Docker, actually. So another limitation of native AOT is that you cannot compile across operating systems. Because that binary you're creating is specific to that operating system, it needs to know of the operating system libraries that can make and actually interact with that specific operating system. And because AWS Lambda runs on Amazon Linux, specifically Amazon Linux 2, and I'm guessing not many of you are using Amazon Linux 2 for your .NET development, we updated our tooling to allow building on a Docker container seamlessly. I mean, it's just the exact same deployment process you do for a non-native AOT app, right-click deploy, or it maybe you use Amazon Lambda tools from the command line. It's all really the same thing under the hood, so it all works. Hopefully we can maybe, I might have been too late, but I wanted to show you the container here, but you'll see it actually deletes the container when it's done with it, so nothing to clean up there, although it will download that image. We provide a default Docker image for builds depending on your target framework. So we can now actually do, with this feature we added, it actually gives you the ability to do Docker builds not for native AOT too. If you want to do a container build for all your Lambdas, by default, you can just set that property in your defaults JSON file here with some of your other properties. And then, first, maybe you have a lot of developers all working on a project and you want to have a consistent build environment and it has certain dependencies. You can do container builds now with these Lambda tools. But what I was saying is we provide a default image, but we also allow you to specify your own if you want to create your own Docker image to do the build on, and you want to install certain environment dependencies in that case. I'll actually show the help text for Amazon Lambda tools here. So if this command line is our extension of the .NET CLI, and it's actually what's running under the hood of the Visual Studio extension. But with this help text, you can see these 3 new Docker-related arguments we created. So there's use container for build, so you can turn on container builds even if you're not using native AOT. I should say we will try to figure out if you are doing native AOT and you're not on Amazon Linux 2, we'll automatically turn that on for you because we know it's not going to work if you don't have that on, so we force that. But you can turn it on explicitly for non-native AOT builds if you want. And then, like I said, you can specify your own container, so that's container image for build. And then the last one I wanted to just briefly mention was code mount directory. So this one's a little subtle. Basically, we need to mount your source code to the container so that it can be built in the container. And we have to know which directory to mount. We don't want to necessarily mount your whole hard drive to the Docker container. It's kind of a risky thing to do. And so by default, we'll start from your entry point, which is where the template points to, and we'll look for a solution file. And so if you have a solution with multiple projects, hopefully all those projects are in subdirectories under that solution. But if not, you can use this to specify exactly which directory you want to mount to the container for building. Hopefully, probably an edge case for most people, but good to know it's there. So let me, okay, so our deployment's complete now. The other thing I wanted to say about building and deploying native AOT is that because we're doing everything ahead of time, it's pretty resource intensive. For an app like this, a Hello World Lambda, you can probably build that in less than 10 seconds for a .NET 6 or .NET 7 app. But with native AOT, it can take like 2 minutes, like a minute maybe. It takes a lot longer to compile because it has to do all that trimming and all that optimization ahead of time. But then you get that benefit at runtime, and so you can get those cold starts down. And with that, you could potentially need to scale up your Docker containers or your build machine to make sure it has enough RAM to actually do those builds. Because it is, when you're compiling native AOT, it's a pretty intense process. So just keep that in mind. If your build seems to hang, it could just literally be you don't have enough memory. So with the serverless deployment, it spits out a nice URL right into Visual Studio, and you can see our function returned hello AWS Serverless, so it worked without any changes. Okay, we have a couple minutes left. I can show the SAM CLI. So that was how to deploy just a Lambda through right-click in Visual Studio, but you can also do a similar thing with the deploy function command here. But we also added support for the SAM CLI. So if you use SAM or the serverless application model to manage some of your infrastructure along with your Lambdas, we also have a blueprint in there, which you can find with SAM init. A quick start, hello world, not Python. And it's actually the #1 runtime is AOT, .NET 7. So, we got lucky with the alphabetical list there, I guess. So again, it's just the same blueprint pretty much as what I just showed, but with a SAM template, and you can use SAM build, which actually calls into the same Amazon Lambda tools code that does the build in Docker and does all that. And then you can run SAM deploy guided probably your first time if you want to try that, but I'm not going to go through a whole nother deployment right now. So I think hopefully that's a lot of information on native AOT. It's pretty different from compiling normal .NET 7, but hopefully that gives you enough to get started and start playing around with it and maybe do a benchmark of your own Lambdas, and we would love to hear the results, good or bad. Did it work for you? Did you have any problems? So definitely let us know. If we could go back to the slide, we just have our closing slide here with our contact information. Yeah, so thanks again. These are our emails and some social media handles. Again, we'd love to hear any feedback, any comments, anything you've actually done with any of these performance improvements. And if you would, please fill out the survey. We're very data-driven and customer-centric, and we want to improve reInvent every year and make it even better next year for you, so that data really helps us if you could fill out that survey.
Yeah, we'll open for questions now. Like, we'll take.
Yeah, thank you.